Welcome, class. I'm Thomas Brandt. This is Mae30a, Group 3, Homework 2. So I'm doing the problem A. So this one we just had to draw a free body diagram. This is what we were given, and this is what we did. So there's going to be a tension force along each of the strings, the ropes, the wires, and they're going to be in the direction of where everything's being hung from, where the wires actually attach at point A. So we have one on TBA, TCA, TDA, and then we also have the weight force of, here we're just considering this big square down there. That's the weight force, and that's going directly downwards. Software is a little annoying finding the angles, but we got there eventually. You can just solve for those using Hw2 and that sort of stuff.
So you just used triangles within these.
Yeah.
Okay,
So
yeah.
I think most of them we created these two triangles, one on the floor, and then we get this distance here, and then we can use that to get this triangle of this middle part, and then the wire.
All right. How come the tensions are pointed up?
So we're always gonna point the tensions upwards and to where it's connecting, where it's being hung, like that. And that makes sense because they're counteracting the weight force, which is downwards. These all have a y component pointing upwards, which we'll use in the following question. Make sure to say your name. I think that matters.
I'm Evan Fogel, the number 2. Well, part 2 of the first question. So my approach to this was by breaking all of these forces into their Cartesian vectors. And so
What's the word of the day?
Word of the day, term of the day, Cartesian vectors.
Yeah.
So I just showed a formula using the AD tension. So we take the unit vector of AD, and then you can multiply it by the individual directions of it divided by their magnitude. And
So how did you derive those components?
So you could... Okay, I understand your question. You get those, so these... Can you, edit that out?
Do we need to restart?
No.
Okay.
This is concept.
I needed a second to think
That's a
about
good
that.
discussion.
So these individual parts, they come from the distances here. So for TAD, because we're using that one for the example, we have 250 here, that goes there. The height of it, the y distance is 480, and then 360 in the z direction. So that's how you get these, and then the magnitude is just those Pythagorean theorem. You square them and then square root.
How come the 480 is negative, or is that just within reference of how?
Well, the 480 is negative. Hi, I'm Case Rowan. Basically, because we have an origin point here, 0, 0, 0, and we have.
Wait, where's the origin? The origin's right.
Yeah.
Oh, you're setting
Considering
the
that
origin.
0, 0, 0.
Oh.
So from going.
Are you setting the origin with respective at A or the respective at this point right there?
Oh yeah. No, you're right. Yeah, that point. You're right. Yeah, the middle point. So when you go from A to C, TAC, you're going down 480 units. That's why it's negative 480.
That makes sense.
All right, and so when you solve this out, you'll get these three
XYZ components.
XYZ components. And so I just showed it for TAD, but you go through all three tensions and you'll get these. And so the only thing that's given here is the tension of AC, and so you can plug that in here. And so you've got two unknowns, and you can create a system of equations with that. And so if the given was 69 newtons, you'll then get 971 newtons as the weight of the plate.
Very well. Any other questions? I think that makes sense. Okay, so I was going to talk about an alternative way to do this problem. So Evan's approach was with unit vectors and using the tension as the magnitude of each vector.
Say your name.
Did I not? I'm Andrew Thompson, by the way. And I was looking at it as this is definitely not an advised approach, but it is just another way to look at the problem. If you don't want to look at it through vectorization, you can look at it through kind of how Thomas was talking about with the three-body diagram in terms of finding the angles, turning each tension or wire into a triangle. So like if we take this AB component that I've drawn out here, we can have the AB triangle right here. So then you're going to create one triangle that's flush with the XZ plane. So this is the XZ plane right here, and then this is the wire, and then here is the y-axis. And you can use this to find the components of then this triangle, which this is flat on the XZ plane, so this would be like right here. It's kind of hard to visualize it with this diagram. It's all right. And then you can find components of the x, z, y, create another system of equations, but this is notably going to be a lot more ugly, for lack of a better word, because you're going to have a lot of angles, like you're going to have cosine and sine stacking up against each other. So I would definitely think the unit vector approach is going to be better, but this is just another way to look at it, because conceptually I think this makes a little bit more sense to me. But yeah, so that's just another way to look at that problem.
Okay.
Questions, comments, concerns?
Wait, sorry, where is that second triangle in this diagram?
Okay, so this triangle is flush with the XZ plane, so it's kind of hard to, you could draw it like right here. So
it's this triangle here.
Yeah, so
Okay,
this
okay.
is, so you see the 320 right here, and then the 360, so this is the 360, the 320, there you go, thank you, that's beautiful.
Okay.
Thomas
Yeah.
Brandt.
That makes a lot of sense.
Yeah, so that's just another way to look at that problem, but yeah.
Okay.
Well done.
Let me get a chair real quick, actually.
Here, you can just use this one.
Are you sure?
Oh,
That was clean.
Okay.
That's nice.
Hi, my name is Case Rowan, and this is problem 3 of my homework. Okay, so we're given this skier that's on an incline supported by 2 tensions in 2 different ropes. And in this drawing, we set this little corner here is the origin, and we have points A where the skier is, and B and C where the ropes connect to. So we have points A, B, and C using the origin. We can get the coordinates for every point and set up vectors AB and AC by subtracting the what was
Head
that?
minus tail.
Yeah,
Tip minus
yeah.
tail.
Thank you. And then we get these 2 vectors AB and AC, and we can figure out the components using the unit vector, just as Evan showed in the past problem. So these
So
are
it's the same kind of approach as the last problem.
Yeah, exactly. But here we have a third kind of vector, which is the normal force of the skier. So this is like a 2D cross-section view of like the whole thing.
Okay, I like this.
Yeah. So this is the skier, and his normal force is normal to the plane he's on. So it's actually at an angle. And if we set this as theta, we have our 3 sides, or I guess we have 2 sides, and using, what was that, Pythagorean theorem, we can find the third side.
Yeah.
So using triangles and all that, we can say that basically you get this angle as theta using similar triangles. And so now we have n, the y component of n, and the x component of n, which are just sine theta and cosine theta. So we, after like doing the unit vector stuff, we get that our vectors n, sine theta, cosine theta, and 0. But since we don't know theta, we can just say that sine is opposite over hypotenuse because of so, and then ka for cosine is adjacent over hypotenuse. So using these sides.
Okay. So you don't even need to find the angle.
Yeah,
That's really
exactly.
nice.
You could probably use angles, but I think
It's simpler.
It's much easier. Yeah. And then you can just convert that to decimal. So now we have 3 vectors, and
Sounds like a system of equations to me.
exactly. We have our perfect system of equations, and using our third z forces, we actually see the relation between TA and TCB, or TAC and TAB. Yeah, so, sorry. TAC is actually 2 times TAB. And so if we solve for one of them, we can easily solve for the other one. So using the system of equations, we find that TAB is 30.25 pounds. And then just doubling that for TAC, we get that at 60.5 pounds.
pretty similar to the last problem.
That is
Yeah.
pretty similar, except
I
throws
think
you off as the-
visualizing the normal
Yeah, yeah.
component is definitely
most
the
definitely the
the
hardest
spin,
part.
the
Yeah,
harder
yeah.
part. Yeah. All
Yeah.
right.
So
Oh,
when you
wait,
made
one
your
more question.
original ABC points, and you
Uh-huh.
so you did that all with respect to the origin, right?
Yes, this little corner here.
Would it be better or worse, or what would you think if you made like point A the origin, for example?
I think because the problem actually labels this as the origin, it does that for a reason, so you should probably just use that as the origin.
I think
I think it's the easiest method.
I think conceptually you could make that the origin. I think it would just be hard transitioning, like moving each coordinate respective to A as the new origin.
Yeah.
So I guess like you could do that as long as you're consistent. I just think that's adding some unnecessary work, maybe.
Yeah, and your A coordinate would be 0, 0, 0. I think originally I tried that, and then I realized that
Realize that was stupid. I'm just
yeah, that was not the right approach. No,
I think that's like valid though. It would make some
You
of the
could.
vectors easier to find, but beyond that, I don't see a
yeah, I think
strength to it.
honestly you could probably do it that way. Yeah, but I think there's a reason that it says O in the picture and labels as the origin, so I would just do that. Any other questions from Evan, or I guess anyone?
I'm so sorry for falling asleep in class. If you get this message.
It's definitely a TA watching this.
He's not getting that message.
should we say your names once more?
Okay.
Thomas Brandt.
Case Rowan.
Andrew Thompson.
Evan Fogel.
And where, group? Group 3. Group 3.
Yeah. Okay. Bye.